Okay, it is the top of the hour, and we seem to have the audio problems that were affecting at least my delivery to everybody solved. So we are going to get started here. Good afternoon. Welcome to today's webinar, Effect of Chemical Dispersants in the Gulf Oil Spill, an interactive webinar for all legal professionals involved with potential health and safety situations arising from the ongoing oil spill in the Gulf of Mexico. During today's presentation, our presenter, Dr. Ken Daugherty, will cover the following: dispersants used in the Gulf oil spill, the effectiveness of dispersants, and the long-term effects of dispersants. Our presenter for today's webinar is Dr. Ken Daugherty. Dr. Daugherty has held various positions in government, industry, and academia. He graduated from Carnegie Mellon University with a BS in chemistry, a Ph.D. from the University of Washington in analytical chemistry, and minored in ceramic engineering. He also holds a Master's of Business Economics degree from Claremont Graduate University. During Dr. Daugherty's military career, he headed a super toxic laboratory with the mission of analyzing worldwide samples of nerve agents, riot control agents, hallucinogenic agents, and toxins. Colonel Daugherty was awarded the Army Commendation Medal, the Army Achievement Medal, and 2 Army Meritorious Service Medals for scientific achievements. In academics, Ken serves as an associate professor at the University of Pittsburgh and full professor, distinguished research professor, and Board of Regents professor at the University of North Texas. During his academic career, he undertook studies of fuel, drugs, well oil operations, and investigation of organic and inorganic toxins. In industry, Ken has served as the Director of Research and Development and on the Board of Directors of several companies. There will be 2 question and answer sessions during the presentation. If you have a question, we encourage you to use the chat or Q&A feature located on the right-hand side of the screen to submit your question to the presenter. We encourage all attendees to submit questions throughout the presentation. Tomorrow morning, I will send out an email with a link to the archived recording of the webinar. We do ask that you take time to fill out the survey that will appear on your screen after the webinar is over. I now invite you to sit back, relax, and enjoy the presentation. I'm now going to turn it over to our distinguished presenter. Ken, it's all yours.
Great. Thank you very much, Matt. Thank you for joining us, everyone. It's a pleasure to be with you today. As you know, the Deepwater Horizon event occurred more than 3 months ago and really has affected severely the Gulf of Mexico. The history of chemical dispersants use in such oil spills has been going on for many, many years. Dispersants have been used way back in the 50s and 60s. Some of you may recall the supertanker Tory Canyon in southwest England that spilled in 1967. Many types of dispersants were used during that accident. There have been spills off of Australia and Tasmania in 1995, Milford Haven in 1996, a large spill from the sea, Empressol. But nothing really is compared to the spill that has occurred in the Gulf of Mexico. Probably more than 2 million gallons of oil has spilled to this date. Oil plumes of the size of 3 miles wide, 15 miles long, and 600 feet thick have been seen in this spill. Nothing you do in a cleanup effort is without impacts of its own, no matter what type of system you try to use. The sudden introduction of high concentrations of hydrocarbons that are resulting from this oil spill can kill or cause sublethal effects in some marine organisms. In the 60s, as more oil was transported by sea and in larger vessels, the increased risk of a major oil spill was increased dramatically. dramatically. When we start discussing different types of dispersants, one must try to make the correct choice of dispersants, try to accurately calibrate the dispersants in field tests, try to train and have the right competence with regard to application techniques of the use of dispersants, and try to develop more objective and reliable monitoring methods. This is just an example of spraying oil dispersants. The type of oil dispersants that would be used in the sea are not the same as the type that would be used on land. Generally, a dispersant consists of a surfactant or a detergent of some type, a solvent to hold the surfactant, and various types of additives or stabilizers to keep everything in place. The composition of an onshore dispersant is going to be different than an offshore dispersant. Dispersants are just one part of a strategy, an overall strategy to try to go after the accident that occurred in the Gulf. The main goal of the dispersant is to try to prevent the oil from impacting the fragile coastline of the Gulf and influencing wetlands and marshes and beaches. A dispersant is going to attempt to break up the oil and convert it into small droplets and try to speed up the natural degradation that would occur in an offshore manner. What are oil dispersants? Well, they are a common tool. They're certainly used after many oil spills, and there have been well over 1,000 oil spills in over 90 different countries around the world in the last 30 or 40 years. The dispersants try to remove the oil slick. The attempt is to try to increase the rate of biodegradation, which occurs after the dispersant breaks up the oil slick into smaller droplets, and to try to reduce the harmful exposures to wildlife. How do oil dispersants or chemical dispersants work? Well, they separate the oil slick and they break it into smaller drops of oil so that nature can go after then these smaller droplets of oil. The attempt is being made to try to disperse these droplets throughout a water column, generally somewhere on the order of about 10 meters or 33 feet in thickness. Naturally occurring bacteria then go after these droplets, and the attempt then is, of course, to try to protect the fragile coastal areas. The next slide is a diagram, a rather complicated little diagram, but a diagram of how oil dispersants work. If you take a look at the top left corner of the diagram, these are the dispersant droplets that contain the surfactants, which are sprayed or somehow applied onto the oil surface. The solvent then in B carries the surfactant into the oil. If you notice in that round ball up in the upper right-hand corner with the red dots, these are kind of like straight pins. The straight pin, the sharp end of the pin, would be some sort of an organic compound which can penetrate into the oil. The round end or the red end of the straight pin is essentially a surfactant, which goes after and tries to bond with the water. So you have a system in which we know that oil and water generally don't mix. This is why the oil comes to the surface, is less dense normally than water, so it rises to the surface. And if you take a look at C, the surfactant molecules are migrating to the oil-water interface, and the surface tension then is being reduced of this oil slick, allowing small drops of oil then to break away from the slick in D. These kind of round balls with the red straight pin sides, the red ends are essentially the surfactant then sticking into the oil droplets. And the oil droplets then gradually disperse by turbulent mixing, wave action, leaving only a sheen, hopefully, on the surface of the water. Oil is a very complicated material. I worked on a project many years ago with a fellow by the name of Dr. Frederick Rossini, who headed up the project, distilling the natural components which are present in Oklahoma crude oil. And at that time, we were able to distill off and purify at least several hundred different types of compounds which are present in oil. If you then try to break the oil into even smaller amounts of materials and get into its components, one can get into the thousands of different types of materials that are present in oil. Oil itself consists of paraffins, things like methane, ethane, hexane, and so forth. It can consist of aromatic types of compounds, such as benzene and naphthalenes. Consists of various types of naphthenes, like cyclohexane and cyclopentanes. Various types of alkenes, like ethylene and butene and isobutene. Various types of dienes, like acetylene and butadiene. It's a very complicated material, largely consisting of carbon. About 84% of petroleum is carbon, maybe 14% of it hydrogen, and then smaller amounts of sulfur, nitrogen oxide, oxygen. There are some metals in it as well, things like nickel and vanadium, which kind of mess up the procedures which one uses then to clean up oil spills. Various types of salts can be in oil as well. So it's a very complicated material, and depending upon the type of oil, one can then determine the different types of dispersants which must be used to try to work with that oil slick. How do these surface reactions work? Well, if one assumes that oil droplets are spherical, and if we do assume they're spherical, then one can use the volume equal to 4/3 pi r cubed for a sphere, the surface area equal to 4 pi r squared. And if we reduce the radius of the droplets by a factor of 10, of course the volume of the oil will remain the same, even though the droplets are getting smaller. And if we go by a factor of 10 to reduce the size of the oil droplets, in other words, make the diameter of the droplet 1/10 of what it was, then the total number of droplets is 1,000 times greater. But the total surface area increases by a factor of 10. So if you have a given amount of oil and you reduce the size of the droplets and you make the droplets 10 times greater, then you're increasing the surface area by a factor of 10 as a result of that. Why is that important? Well, one of the reasons is if I were to take a nickel out of my pocket and I drop it on the floor, nothing happens to that nickel. But if I take that same nickel and I grind it to a very fine dust and make that nickel into very, very small particles, and I try to drop that same nickel but now as particles onto the floor, it will immediately burst into flames. The reason for that is that the surface area is much greater. And with a greater surface area, the rate at which the oxygen is reacting with that surface is much greater. The same thing is true with an oil dispersant. When you make these droplets into smaller size materials, the surface area increases, and the bacteria can now attack a much larger surface area, grab hold of those molecules, and start to degrade them. In the process, of course, a lot of oxygen is consumed, and many times one will see through the use of dispersants and through the oil degradation process that the oxygen is depleted in the environment or in the water column that surrounds the oil slick. So it's a complicated process, but the important thing to remember is that with the use of dispersants, the surface area is increasing, and as a result of that, the rate of bacterial attack increases as a function of that. Now, if we take a look at the BP oil leak, there really have been just two heavily used dispersants. They are both made by Nalco Chemical Company. One is Corexit 9527, and the other is Corexit 9500. And in fact, when I looked at the latest statistics of how much oil has been used, or how much dispersant has been used since the accident occurs, approximately 1.83 million gallons have been used of these two dispersants since the oil accident occurred in the Gulf. So they have been used quite heavily. If you take a look over the last week or so, however, the amounts of dispersants that have been used is pretty minimal due to the cap, which is now on the well, and also due to the fact that a lot of the oil slicks have aged. One of the things you find out very quickly through the use of dispersants is they have to essentially be used on fresh oil slicks. They are not so much used as the oil slicks age. If we take a look at the composition of the Corexit 9527, it consists of 2-butoxyethanol, propylene glycol, an organic sulfonic acid salt, as well as other types of ingredients that act as stabilizers for the overall system. One of the problems with Corexit 9527 is the 2-butoxyethanol, which if you go into the chemical abstract data and take a look at the material safety data sheets, this turns out to be problematic with regard to that particular material. So as a result, the 9500 is a better choice probably from a toxic standpoint. It consists of distillates, petroleum hydrotreated light, propylene glycol, which is also present in the previous slide, and also an organic sulfonic acid salt. So these are being used then as the main dispersants in this system. One can then take a look at the chemical abstract data sheets and look up all the different materials that are present in these two primary dispersants and take a look at all the effects from a toxicity standpoint in the chemical abstract data. And I think, Matt, at this point, you wanted to ask some questions?
Yeah, we have a couple questions, and for those in attendance, if you'd like to submit your questions to Ken, please use the chat or Q&A feature, which is found on the right-hand side of the screen. We have a question here from Brian who asks, why is timing so critical with regard to applying oil dispersants to the oil slicks?
That's a good question, and the timing is critical because as the oil slick ages, and remember these oil slicks can be very thick. Initially they can be 20 millimeters thick. As the slick disperses a little bit, it can be 1 millimeter down to a tenth of a millimeter less thick. And when the slick is new or is first applied to the surface of the water, a lot of the volatile components, the various components that we mentioned before, of the hundreds of different types of components of the oil, the methane, the ethane, and so forth, these will volatilize very quickly, leaving behind the more aromatic materials, which are heavier, which are more dense, which are more difficult to break up in the oil. And as a result of this, and also as a result of photooxidation, which occurs from the sunlight and the slick thickness, all these factors influence the use of a dispersant. And as a result, because of these factors, the dispersant forms these droplets much more easily when the oil is fresh, as opposed to allowing it to age.
Okay, great. Thanks, Ken. We do have a question here from Jenna who asks, is there a chance that dispersants can be carried through the wind onto the land further north?
You mean as a result of evaporation?
let's operate under that assumption, and I'll seek clarification from Jenna.
If we're talking about most dispersants, or particularly the two that we've just talked about, the corrected dispersants, these are not really highly evaporable, and as a result, they will not get up into the air and will not be taken by the winds and so forth. They will get into the water column. Just about 100% of these dispersants will get into the water column and will not be dispersed through the air.
Yes, she was asking through evaporation, so I believe the question was answered. Thank you, Cam. We have a question here from Lynn, who asks, how long will it take for the dispersed oil to break down into relatively harmless compounds? I understand that lighter ends disassociate in sunlight, but it seems this oil is mostly below the surface.
I think that's another good question. Probably it depends upon a lot of different factors. It depends upon the types of oil. And we'll talk a little bit about this a little later on if I don't answer this question as the talk proceeds, because I was planning to try to tackle this a little later on in the talk. Perhaps we could come back to this question again.
Okay, great. Those were great questions, and keep the questions coming in. I don't see any other questions in the queue, so why don't we move on with the presentation of content, and we'll take another question and answer break after we're finished up with the content. Okay?
Okay. Thank you, Matt.
Yep.
The next slide just is an example of what we have been talking about, the oleophilic part of a dispersant, which is essentially the part which goes into the oil, the hydrophilic part, which associates itself with water. And we're going to start talking about how effective some of these dispersants can be. One of the ways to try to look at the dispersants and these surfactants is to run tests on them. I did some work many years ago, and these same tests and the same way of looking at surfactants are still being used today. Essentially, one way you can evaluate what a surfactant can do is to take a shake flask or an Erlenmeyer flask, and you go out to a activated sludge plant or wastewater treatment plant, and you get some of the actual sludge water which is present in that wastewater treatment plant. You bring it back to the laboratory, and you start feeding that sludge various types of nutrients, things like bone meal and so forth, allowing the bacteria which are present in the sludge to start consuming that material that you're feeding it. Gradually, over a period of time, you start weaning away the food that you're giving the sludge, and you start introducing surfactants to it, gradually increasing the surfactant to food ratio, so that finally the bacteria that are left in that flask have to live on the surfactants. And then by various techniques such as mass spectroscopy or infrared or thin layer chromatography or whatever techniques you choose to use, you can then start measuring what has actually happened to the surfactant. And probably some of you know it a long time ago that manufacturers used to make surfactants which were called linear alkyl sulfonates, as opposed to those which were the benzyl sulfonates. And it was found that the linear alkyl sulfonates broke down and were degraded much more effectively than were the ones which contained the phenyl group. And as a result of that, surfactants today largely are made with the linear alkyl groups. I did work on this particular surfactant. This is a nonyl phenyl ethoxylate. It's called a non-ionic surfactant, just because of the ingredients that are present in this particular structure. And when you start looking at how this material behaved in one of these shake flask tests, it turns out that if you look at the left-hand side of the molecule, this is the nonal group. In other words, 9 carbons. Each of the little bars represents 3 carbons that are in a vertical position, and you have a hydrogen connected to the end of it. In the center of it is a big phenyl group, and then over to the right are these ethoxylate units. These ethoxylate units can go up to 50 or more in length. Generally, in a lot of different surfactants, they can be down around 10 or 20 ethoxylate units. This is the CH2, CH2O in parentheses, and then with an N, the N then represents the number of ethoxylate units. It turns out when we looked at this particular material in a shake flask test, it turns out that the bacteria, when they start eating this particular molecule, they like to eat it from the right-hand side, and they start chomping on the ethoxylate units. And they go up and proceed down, and they start chopping these ethoxylate units off, consuming them, producing in the process carbon dioxide, and the ethoxylate units gradually get down to maybe 2 to 4 ethoxylate units. Then the bacteria turn around and they go to the other side of the molecule, and they start eating the nonal group, and they gradually start consuming the carbons off of that end of the molecule. Then they start looking at the phenyl group, and many bacteria have trouble with phenyl groups. And as a result, petroleum contains many phenyl groups, in particularly these various aromatic types of compounds that are parts of the overall composition of petroleum. And as a result of that, these phenyl groups remain, and they stay and are not easily biodegraded. So this becomes a real problem. The effectiveness of how well these dispersants degrade these types of compounds relates to the oil properties. It relates to the thickness of the slick. It relates to the dispersant to oil ratio. Many times these dispersants are used in the ratios of about 1 part dispersant to about 10 to 50 parts of oil. The surfactant loss at the water surface, the surface tension of the slick on the water, the wind and wave energy, because the more wind and wave energy that you have, the more turbulent mixing that you get of these materials, the emulsion formation or the micelle formation of these various droplets that we talked about before, and also the salinity of the water has a big effect on how much salt is contained within the water. These all bear an important role with regard to the effectiveness of the dispersant. The biodegradation rates depend upon the dispersant which is used and how well the oil is dispersed, how well there is always oil left over that is non-dispersed, and also the type of dispersant which is being used. Considerations that are important when using dispersants include the oil characteristics, the sea and water conditions and weather. If you don't have a lot of wind and turbulence, sometimes it's difficult to make these dispersants work properly. And also you have to be very aware of the surrounding environmental sensitivities. For instance, the United Kingdom will not allow dispersants to be used within about a mile of shoreline, because you don't want these things coming up on the shore. They are meant to be used out in the ocean or out in the sea. The environmental toxicity of these various types of materials, whoops, went the wrong way, sorry, apologize. The environmental toxicity of the types of dispersants which are being used depends upon the, whoops.
Ken, is there a problem?
Yes.
What can I help you with?
Lost the screen, Matt.
Okay. Do you have it, here, let me take over control real fast. Okay, and I'm going to send it back to you now. Do you have the screen back?
Not yet.
Okay. Well, you're on environmental toxicity. So if you want to go through that slide, I'll try to get it back to you.
I will. The environmental toxicity of the various types of dispersants is going to depend upon the species of wildlife that are present, the life stages of various types of marine organisms and the benthos, the duration of exposures, the water temperature, the concentration of the dispersant, the geography, and where the dispersants are being used and the type of water body, as well as human toxicity effects. And I believe the next slide, Matt, and I don't see it on my screen because I can try to check back in, but I think that the next slide is the plane over the slick.
That's correct. Yep, the plane over the slick, which is now on everyone's screen. So.
And also the next slide is a boat applying dispersant.
That's correct. Yep.
I think in this particular slide, the spray arms are mounted near the bow of the vessel. The next slide, I believe, is of the helicopter. And
that's correct.
This is a picture of a helicopter applying dispersant with a kind of an underslung spray bucket system applying the dispersant to oil slicks. The next one is a shoreline application, such as was used in the Sea Empress incident in the United Kingdom back in 1996. And I think there's one more slide of a plane releasing dispersant as well over the sea.
Correct, yep.
The next slide, I believe, is of Corexit.
That's correct, yeah.
And the applications of it, it's generally supplied at about 2 to 10 gallons per acre. 1 gallon of Corexit is applied for roughly every 10 to 50 gallons of oil that is spilled. The costs of Corexit back in probably about 2002 were on the order of about $15 to $20 a gallon. Today they can be upwards of up to about as much as $50 a gallon. I believe that NALCO estimates that I think I have seen a statement of NALCO that says it is about 1% of their total revenues is being used for oil dispersants, and their total revenues are somewhere, I think, on the order of about $4 billion. So that would mean somewhere on the order of $40 million NALCO has put out with regard to the dispersants that they have on hand. And they are making more. All of the dispersants that NALCO is now generating, I believe, are of the 9500 variety, the 5500 variety. The previous material that they had available and what they first started with was the 9527, and I think that they have used up just about most of their stocks of the 9527, which in my opinion is more toxic than the Corexit 9500. So as I mentioned before, they have used about 1.83 million gallons of Corexit, both for surface as well as for subsea. The next slide, I believe, is on the monitoring and how one goes about monitoring the use of various types of dispersants. One has to take a look at dissolved oxygen, which of course is very important with regard to marine life. Matt, I assume that you are on the monitoring slide now?
That's correct. Yep, the monitoring slide is up on everyone's screen at this point. Yep.
Thank you. One of my problems is that I live on an island up in the northwest, and every once in a while the satellite goes down, and I'm afraid that's what happened during this talk, and I apologize for that. There are also CTD rosettes which are used with regard to monitoring activities. The C stands for concentration, the T for temperature, the D for essentially depth, which is also a measure of pressure. one can imagine that this oil spill, which is occurring at the deepwater horizon, is occurring at a depth of 5,000 feet, and roughly for every foot of depth of water that you go down, the pressure increases roughly by a half a psi, so that by the time you get down to a depth of 5,000 feet, you're looking at pressures on the order of 2,500 psi or more. So it's a much different environment than what you have on the surface of the water. Toxicity tests need to be run on all these materials: conductivity, temperature, depth, light, fluorescence, oxygen, turbidity, and also one needs to be concerned about the LC50s, or the lethal concentrations of these various materials which are being used. One can get, of course, all this information by looking at the chemical abstract service numbers. There are a lot of dispersant unknowns with regard to looking into the future. The long-term effects, largely, of dispersants are unknown. The correctant materials have been used for probably about 20 years now, but of course much longer periods of time have to go by with regard to looking at carcinogenic effects and teratogenic effects and mutagenic effects and so forth, as to what effects these have on dispersant unknowns, the fish larvae, the oysters and mussels, benthos, organisms that are very low on the food chain, water repellency of birds. Of course, lab studies do not equate to field studies. Many times you get tripped up by doing laboratory work and you find out that things are not the same in the field. So field studies have to be continued as well. And then the effects of wind and wave on chemically treated oils. So the general discussion now with regard to present day, the future, and long-term effects, these things I think will continue for many, many years. And the EPA is going to be working with NOAA, with the Department of Interior, with British Petroleum, and of course with the U.S. Coast Guard, and issuing directives and evaluating the current situation with regard to what can be done. And as a result of that, when we start looking at a summary of the chemical dispersant use, the chemical dispersants enhance the natural breakup of oil. They remove it from the surface down into the water column, as we talked about, maybe down to a depth of 30, 35 feet. They dilute the oil spill, the oil slick. They gradually biodegrade it by increasing the surface area of the droplets, which are being produced as a result of the use of the dispersant. And the hope is to minimize pollution and damage to the sensitive coastal areas. And I think I would like to try to answer any more questions that anybody has, and I think this generally concludes my talk. Thank you.
Great. Thanks so much, Lynn. What a great presentation. If we could we go back to the question that was posed by Lynn during the last Q&A session? How long will it take for dispersed oil to break down into relatively harmless compounds? I understand that lighter ends disassociate in sunlight, but it seems this oil is mostly below the surface.
Yeah, I think that it's a good question, and I think that as we talked about the different types of components which are present in oil, those which are linear and which do not contain the phenyl groups and so forth are going to break down much more easily, and I would think that the majority of those are broken down very early on, let's say about the first week or so of dispersant use. You have some of those compounds, though, which are the cyclic unsaturated variety, and these are not going to be attacked very easily, and they're going to gradually get down into the seafloor. These are the types of materials, I think, that are forming the oil balls and so forth that wash up on the shore. And it's going to take, in some cases, everybody remembers the Exxon Valdez accident back, I think it was in '89. This has been going on now for 20 years or more, and some of these massive oil balls which wash up on the shore can still be found today, so these do not degrade very easily. So it's a very complicated answer to a good question, but I think that it's not easily answered. It's going to be a matter of time, and with time, gradually, of course, more of these oil components degrade. And the more phenyl groups, the longer it's going to take for the oil to degrade.
Excellent. We now have a question from Charles who asks, how long do you think it will take, or how long do you think it will be before we know the long-term effects of these dispersants on humans?
Once again, a good question. And you know that the corrected formulas have been published and they're online, so you can get all the components that are present in corrects at 9527 and also corrects at 9500. But still, like many different types of chemical compounds, the very long-term effects are not known. And one just has to look at a material like asbestos, which, I mean, there were reports back in 1918 that asbestos was harmful to the health. And that's, 90 years ago, but we're still suffering from the effects of different types of asbestos and mesotheliomas and so forth today. So many of these things are going to persist for long periods of time. The long-term effects are going to be hard to quantify, and it's just not an easy question to answer when you start having to consider effects like mutagenic, teratogenic, and carcinogenic types of effects. Agent Orange, for example, and dioxin are still being studied, and of course that was used during the Vietnam War. I think we have a similar situation with oil spills, but of course in my opinion, I don't think most of the components of oil are anywhere near as toxic as asbestos would be or as dioxin would be. And I'm not sure I'm doing a good job in answering the question, but it's a very complicated answer to that question.
Right, and a follow-up to that, Charles asked, and does that time period, so kind of the unknown time period that you just laid out, does that fit into the 3-year time period that Ken Feinberg has suggested?
I think it's going to be longer than 3 years.
Okay, great. We now have a question from Mark who asked, are there any dispersants that are 100% biodegradable, and do they all have a negative impact on the environment?
Well, as I hope I mentioned right in the very beginning of my talk, there is nothing that you can do in a cleanup effort which is not without impacts of its own. So as a result, you can design surfactants, and they are being designed. For instance, the ones that are being used without phenyl groups, for example, is a big step forward if you get into linear alkyl groups, because these do biodegrade much more easily. So when you start designing these various types of dispersants, you have to keep all this in mind, but at the same time you want it to be effective as well. So you have some trade-offs which occur. And bottom line is that the more linear you can make a molecule, I think the more effective it is with regard to biodegradation itself and disappearing. The more phenyl groups and other types of groups that you put into a component, the less likely it is going to be that they're going to biodegrade very easily. So once again, it's a rather complex question. You can design them to degrade easily, but they may not be effective. Or they can be very effective, but not quite degrade very easily. So you have to, it's a balancing act.
Okay, we now have a question from Lynn who asks, if I were a commercial fisherman filing a claim with BP, how long should I assume that fish caught might be unsafe or have exposure to these dispersants? He realizes it's complicated, but the claims process requires a timeline.
That's a tough question. I'm not sure I can just give an offhanded answer to it. It's going to be, in my mind, after several months, I think that the concentration of various types of chemical compounds which can get into the various types of sea life is probably going to be not a problem from a bioaccumulation standpoint or from a toxicity standpoint. It's, for the most part, it's not like inorganic materials like mercury and nickel and so forth, and cadmium, materials that can build up within an organism and bioaccumulate. A lot of these things, I think, are going to be, for the most part, biodegraded, and I would feel relatively safe, I think, in eating organisms or eating fish that after a several-month period of time.
Okay, we have two more questions from Charles, and I would encourage all the attendees out there to submit their questions. I think this Q&A session has been very good. Charles asked, his first question is, what medical specialty do you suggest a person exposed to these chemicals be examined by?
That's a good question. I would think that probably you would want to have blood and urine tests done, and that could be done by a lot of different laboratories around the country. And what was the second part of that question, Matt?
Sure. And then he asked, does it matter whether the person is exposed via inhalation, ingestion, or skin absorption?
I don't think that inhalation would be a problem, because for the most part, as long as when you're applying these dispersants, of course, they have to be applied in the correct manner. And what does the correct manner mean? I would not want to work around these types of materials unless I had the appropriate types of protection gear. What type of protection gear? Well, I would want nitrile gloves. I would want or polyvinyl acetate types of gloves, alcohol gloves. I would want skin protection. In other words, some sort of means in which I was wearing apron and boots, which were essentially impervious. I would want the appropriate type of hygiene present. In other words, some eye wash fountains, safety showers, and so forth that were available. So I think the important thing is when these materials are being used or applied, that you have the right type of protective gear so that you don't get it on your skin, so that you don't inhale it, and so that you're not around these materials to breathe in any vapors which may be present. So you would not want to be applying these or any other dispersants. There have been roughly 18 of them, last count I think, that have been approved by the EPA to be used. Of course, the majority of them are these two correctant materials, the 9527 just because it was available and there were large stocks available, the 9500 because it is now being produced and replaces the 9527. But these are not materials that you generally want to breathe in, absorb, or get onto skin. So you want the right type of protective gear when applying them.
Okay, great. We have now a question from Paul who asks, how long will it take a dispersant to directly affect the oil? For instance, the oil that is deep in the water. If a dispersant is used, will it go down to the deep oil or stay on the surface?
Boy, that's a good question. There are subsurface dispersant techniques used to try to get at oil at deeper depths. They can also be, of course, generally applied on the surface. And once again, you have to take into account that the faster that you can apply these dispersants to a fresh oil system, the more likely it is going to be that you're going to be able to convert these into droplets which can then be faster biodegraded. And the droplet size, which is probably the optimum droplet size with regard to biodegradation processes, it's on the order of about 45 microns. But these droplets can get down to below 1 micron in diameter, and they can get above 100 microns in diameter. So I would hedge a little bit with regard to that question in that I would need more information as to what types of dispersants were being applied, what depths we're talking about, how it is being applied to the oil, and it's not an easy answer. It's not an easy answer to that particular question. That's a tough question.
And then a follow-up from Paul who asked, do dispersants stay in the water for a period of time and continue to work, or do they degrade?
No, the dispersants themselves, just like the oil components, even if you did not apply an dispersant to oil, it's going to gradually degrade, both due to photodegradation, due to just breaking up on its own. All the dispersant does is to try to break it up into smaller droplets, so you increase that surface area and you get a faster rate of biodegradation. The dispersants themselves are forming these various micelles, and they are going to be degraded as well. And of course, the optimum thing is that you want to develop dispersants that themselves are going to completely biodegrade, and they will over a period of time.
Okay, we now have a question from Clinton who asks, are there any potential carcinogens or other known health hazards that could be created by the dispersants reacting with the atmosphere or water?
I don't think so much in the atmosphere, because I don't think the dispersants are really going to get into the atmosphere they are made to essentially not evaporate very easily. But you have to look at the chemistry of, and when you're considering that oil contains several thousand different types of chemicals, and also the oil contains nickel and vanadium and other types of potential catalysts that can accelerate the formation of different types of molecules. There is a potential for molecules to be formed which could be mutagenic, teratogenic, or carcinogenic, probably in very low concentrations, but that isn't to say that they can't ultimately be formed. Most of the material is going to be biodegraded, but there, I think, is some long-term risk.
Okay, we have a question from Charles who asks, how much exposure time is necessary before permanent injuries can occur, assuming the person is using, handling, and spilling on the deck and his clothes undiluted 9500 and 9527 for several hours a day, a week, or 2 at a time?
Wow. I don't know. That's a good question. But you'd have to really know the circumstances with regard to a particular event, I think, to properly evaluate that. As I say again, you don't want to be using these materials unless you have the right type of protective gear.
Okay, we have a question now from Ryan who asks, why haven't the chemical formulas for dispersants been disclosed publicly?
Well, they have, actually. You can find a complete summary of the Corexit 9527s and the Corexit 9500. It's available online. It's published by NALCO, and it lists the various types of Corexit ingredients, not just by calling it sulfonic acid salt or whatever, but by the actual chemical name, and also giving the chemical abstract numbers as well.
Okay, great. And we have a clarification from Charles for the question previous to the one you just answered about how much exposure time is necessary for permanent injury. There was not proper protective gear provided to the workers. so they were not wearing proper protective gear. How much time, if they were exposed to undiluted 9500 and 9527, how much, and they were exposed for several hours a day, would you say that it would take? How much exposure would it take?
Well, that's a good question. I'd really need to know more about the circumstances before, trying to just say something off the top of my head. The Corexit 9500 is not near as dangerous, in my opinion, as the 9527, and only because of the 2-butoxyethanol, which is contained within the 9527, which is not included in the Corexit 9500, and I'd say there's some risk there.
Okay, great. And one more question, because I don't see any more coming to the queue. We have a question here from Carol who asks, are dispersants the primary hazard to Gulf marine life?
That's a good question. And in my opinion, you're facing a situation where it's a lesser of two evils. And you don't want to use dispersants unless you have to, but the oil is there, so you want to biodegrade it. And in my opinion, the oil is a much more dangerous material than the dispersants would be, just because of all the naturally occurring compounds which are present in oil. Calculations have been done on the amount of Corexit, which is normally part of the Gulf, and it's going to be, when everything is dispersed completely, of course, if you start considering entropy, we're talking about a concentration of probably less than 30 parts per billion when you consider the Gulf. That isn't to say that locally the concentrations aren't going to be considerably higher. But in my opinion, you've got to use something, and you always got to remember that you can't do something without causing an effect upon something else. So, in my opinion, the dispersants are the lesser of the two evils.
Okay, great. I don't see any more questions in the queue, so we're going to wrap things up here. Ken, would you like to say any additional words, or are you pretty good?
No, I think I'm fine unless there is another question. Thank you. And I really enjoyed the opportunity to talk to everybody today. And
excellent.
I apologize on my end for my part of the slideshow going down.
Excellent. No problems. Technology, it happens, and that's why we build in backups. I wanted to thank everybody for taking time out of their day to spend with us. I thought this presentation was great. Ken, it's obvious that you spent a lot of time putting together the PowerPoint, and it was quite obvious that the attendees came with some excellent questions in tow. So I thank everybody for their time and attention to this presentation.
Well, I want to thank you too, Matt, for helping me with this, and I particularly want to thank Carol Kovaleski, who helped me with the PowerPoint presentation.
Oh, definitely. A lot of hands make small work. So there are a lot of people who are involved in all of these presentations, and we owe a debt of gratitude to each and every one of them. If you'd like to speak to Ken about a case, you can contact us here at TASA. Our number is 800-523-2319, or you can send me an email. I believe all of you have my email address. It's mhyde@tasanet.com. We will be sending out the link to the archive recording of this webinar tomorrow morning. The archive recording will be posted in the Knowledge Center of the TASA website. I will also be attaching links to the other two webinars in this series, so you can check out the archive recording of those if you did miss them. If you have any follow-up questions or comments, ways that we can improve these presentations, please feel free to email me. Again, my email is mhyde@tasanet.com, and we'll do our best to incorporate your suggestions into future events. As I said at the beginning of the presentation, there's going to be a short survey that will appear on your screen after you leave. Please do take a minute to fill that out. That is the only way that we'll receive feedback from this presentation. And with that, I thank you for your time and wish you a good rest of the afternoon. Thank you so much.